Hello! In this video, we're going to start out by defining the positive integers. And then we're going to show that the set of positive integers is an inductive set. Now, in this series, we have been working with a list of 10 axioms for the real numbers. And I'll leave that list of axioms in the description below. So really, we're going to be defining the positive integers as a subset of the real number system. So let's start out with this definition. Suppose I is a subset of the real numbers. We say that I is an inductive set if 1 is an element of I, and for all real numbers n, if n is an element of I, then n plus 1 is an element of I. For example, the set of real numbers itself is an inductive set, because we know that the set of real numbers is a subset of the set of real numbers. We also know that 1 is a real number, and we know for all real numbers n, if n is a real number, then n plus 1 is a real number, right? True implies true is a true statement. That's why condition 2 holds. So yeah, the set of real numbers is itself an inductive set. And so the idea is, we define the positive integers to be the set of all real numbers which belong to every inductive set. So if n is any real number, then to say that n is a positive integer is equivalent to saying that n belongs to every inductive set. And now the claim is that the set of positive integers is an inductive set. Now, to prove that the set of positive integers is an inductive set, what we want to show is that the set of positive integers is a subset of the real numbers. We want to show 1 is a positive integer, and we want to show for all real numbers n, if n is a positive integer, then n plus 1 is a positive integer. So let's start out by showing that the set of positive integers is a subset of the real numbers. To prove that, let's give ourselves an arbitrary positive integer, n. Well then, by definition of the positive integers, since n is a positive integer, this means n is a real number which belongs to every inductive set. So in particular, n is a real number. So what we have shown here is, if n is any positive integer, then n is a real number. And that tells us that the set of positive integers is a subset of the real numbers. So now, let's show that 1 is a positive integer. By definition of the positive integers, to show that 1 is a positive integer, we want to show that 1 belongs to every inductive set. And to show that, let's consider an arbitrary inductive set. I'll call it I. Well then, by definition of an inductive set, we know that 1 is an element of I. And so what we have shown here is, if I is any inductive set, then 1 is an element of I. So 1 must belong to every inductive set. And so, since 1 belongs to every inductive set, we have, by definition of the positive integers, that 1 is a positive integer. And finally, let's show that condition 2 holds for the positive integers. And to prove condition 2, let's give ourselves an arbitrary real number n, and suppose n is a positive integer. From here, the whole goal is to show that n plus 1 is a positive integer. And by definition of the positive integers, to show that n plus 1 is a positive integer, we want to show that n plus 1 belongs to every inductive set. So let's consider an arbitrary inductive set. I'll call it I. Now, since n is a positive integer, well then by definition of the positive integers, n belongs to every inductive set. So in particular, n must belong to I. And now we apply the definition of an inductive set. Since I is an inductive set, condition 2 must hold for I. Meaning, we have for all real numbers n, if n is an element of I, then n plus 1 is an element of I. So this statement works for every real number. So in particular, it must work for the real number n that we have in our proof. So taking n to be n, we have if n is an element of I, then n plus 1 is an element of I. But we know that n is an element of I. That's what we have here. So we can conclude that n plus 1 is an element of I. And so what we have shown here is, if I is any inductive set, then n plus 1 belongs to I. In other words, we have shown that n plus 1 belongs to every inductive set. And so then, by definition of the positive integers, since n plus 1 belongs to every inductive set, this means n plus 1 is a positive integer. And so, putting this all together, we've shown if n is any real number, well then if n is a positive integer, then n plus 1 is a positive integer. So we have verified that condition 2 holds for the positive integers. And we have verified all three things, so the set of positive integers must be an inductive set. And that is exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.